So this chapter is electromagnetic induction, and this is what this chapter is based on. All right, so what this equation tells you is, again, on the right-hand side is causes. On the right-hand side of these equations are causes, and the left-hand side is the effect. So what this is saying is, a changing magnetic field, a time-varying magnetic field, will produce an electric field. Okay? And that's what we're interested in. Okay, so, and Mr. Faraday captures the essence of this in his law, which is called Faraday's law, and we'll see that in a second. Okay? And another thing we'll see is, if you have a moving charge in a magnetic field, it will feel a force, and we can use that to produce voltage, okay, so in a particular configuration. But so this chapter will see this equation, we'll be studying this equation and this part of this equation. Okay. So now let's look at this equation. Now when you do Calc 3, you will do line integrals and so on, okay, and you'll learn something called the Stokes law. So you'll learn that there. But anyway, so there's the here's this equation, minus del B by del T. Okay, so what we'll do is, here's a magnetic field. And what this equation tells you is, let's say we increase this magnetic field, okay? With time, we increase this magnetic field. So, for instance, if you could, here's one way of doing it. Let's say you have a magnet like that, and if you make the magnet move in this direction, this magnetic field will increase, okay? I'm doing a simple picture. All right, so from this equation, now what we'll do is, now what we'll do is, let's take a surface integral. Okay, so we'll draw a surface like that, and what we'll do is so we take the curl of the electric field dotted with this surface and take a surface integral, and we'll do the same thing there. Okay. And Mr. Stokes will, when you do this in Calc 3, this surface integral over this surface, Mr. Stokes will tell you this is equal to a line integral of the electric field going around the boundary. So here's a pretty neat thing. A surface integral, this is a two-dimensional integral, and this line integral is a one-dimensional integral. So the Stokes theorem is equating a two-dimensional integral to a one-dimensional integral. Okay. Now, so when you're taking the surface integral in this sense, you use the right-hand rule. Mr. Stokes tells you that the sense in which you want to go around when you do the line integral is, if your thumb is pointing in the direction of the surface integral, then you take the line integral in this sense. Okay, so that's what we did. We did the surface integral in this sense, but because of this negative sign, you have to go in the line integral in this direction. Okay. All right, so this line integral is, you're taking the electric field going around this loop around there. Okay. Okay, so let's say this electric field is constant, so the electric field, so this will become E times 2 pi r, the circumference of the circle. So in that special case, 2 pi r, and this will be equal to del by del T of B dot dA. This guy is called a magnetic flux. Okay, and this is Faraday's law. And E times 2 pi r, so that is the voltage induced in the circuit. All right, so what we are saying is this time-varying magnetic field produced this electric field. So what is the proof of that? So what if it produced an electric field? What's the big deal? What can you do with an electric field? If you have an electric field, stick a wire there. And if you have a wire there, what will the electric field do? It'll pass a current through it. And you just saw that effect. Okay, so this time-varying magnetic field produced an electric field, and you can drive a current through that. Okay, and you learn that the further out you are, the weaker the electric field gets, and all that kind of stuff. But this electric field is produced, and you can stick a wire there and pass a current through that wire. Okay. All right, so that's the mathematics behind this this thing. All right, so we're going to study time-varying magnetic fields producing electric fields. Okay. Now, the character of this electric field, like I said, this electric field looks like this for this configuration. The electric field is tangent to the circle. Yeah. And this line integral, the line integral of this electric field is non-zero. Okay, it's equal to that, for instance. Now, if these charges, so these charges also produce an electric field in this region. Yeah. Now, you can take the line integral of this electric field around any closed loop, and this will always be zero. Okay, so this is a conservative electric field. Okay. The electric field produced here is a non-conservative electric field. Okay, so that's just a technical detail. I just want to mention that. So the electric field produced by time-varying magnetic fields, its nature is different. It's a non-conservative electric field. The line integral around a closed loop is non-zero. Okay. For this electric field, the line integral of the electric field around a closed loop is always zero. All right, so again, we are studying time-varying magnetic fields producing electric fields. Okay, so here is a practical way of doing it. So you see here's a piece of wire. It's just connected to an ammeter. Okay? And what we're going to do is we're going to move this magnet back and forth. So that will change the magnetic field in this region, and that is producing that electric field like we showed you. And that electric field will drive a current in this wire. Okay, so you're producing current by a varying magnetic field without any batteries. Okay. So when you move the magnet back and forth, you'll see a current. In this situation, what you're doing is you're passing a current through this coil, And that produces a magnetic field. So this is acting like an electromagnet. So instead of a permanent magnet, all you've done is used an electromagnet, move this back and forth, and you're inducing a current in this coil. Okay. And what this shows you is, this is a coil. You're keeping it stationary, and when you close the switch, when you pass a current through this, the magnetic field in there briefly goes from 0 to a maximum value. And while that magnetic field is changing, there's a current induced. Okay? So there's a brief current induced. And once the current becomes steady there, the magnetic field is not changing in there, and then the current will go to 0. All right, so what you want is a changing magnetic field, which is producing the electric field. Okay. All right, so in this chapter, we'll look at time-varying magnetic fields producing electric fields. In previous chapters, we've studied charges produce electric fields, moving charges produce magnetic fields and electric fields. We saw moving charges producing magnetic fields. And now we're going to talk about time-varying magnetic fields producing electric fields. Again, we study charges producing magnetic fields, moving charges producing magnetic fields, charges producing electric fields, moving charges producing magnetic fields, and now time-varying magnetic fields producing electric fields. Okay? All right, so we'll state Faraday's law in a second. So let's first define magnetic flux. We'll do this similar to defining electric flux. You can think of them as the number of field lines threading an area. That's what magnetic flux means. Okay, you can think of it that way. So magnetic flux is denoted by phi, capital Phi, the subscript B telling you that it's a magnetic flux, and it's defined as B dot area, the area vector. So here's the magnetic field vector, and here's the area vector. So in this configuration, the flux through this area is maximum. You can think, again, like I said, you can think of flux as the number of lines threading this area. In this configuration, the flux is 0. And B is in this direction, the area vector is like that, and the angle between them is 90 degrees. So B dot A would be 0. Okay, so now that we have defined magnetic flux, Mr. Faraday tells you the following. Okay. The EMF, this EMF is that line integral that we said, and that's the EMF. The EMF induced in a circuit is equal to negative of the time rate of change of the magnetic flux. Yeah. And magnetic flux, this is just equal to B times area times cosine theta, where theta is the angle between A and the B vector. Okay. So we'll put that expression in here. There is that expression. So the EMF induced in a circuit, which is that line integral, is equal to that. So this is the voltage induced in that loop. So you have a non-zero electric field as long as the right-hand side is non-zero. So now you can do, so all you have to make sure that this right-hand side is not zero. So you don't necessarily have to change B. So Mr. Faraday catches other scenarios as well. You don't have to necessarily make B change with time. You can change area with time. So for instance, you can change the area of the loop, and that'll give you an EMF in the loop. Or you could change theta, the angle between them. Okay. Here's the loop. There's the area, and there's the magnetic field. What you can do is change the angle by rotating the loop. And that's what's done in most practical situations. And that's what we were doing here. See, there's the area vector, and the magnetic field is pointing like that. And you see we're changing. That sound is so annoying. See, in this thing, what we're doing is changing the angle theta. Okay. So this is what we are changing. Okay. And in all practical situations, that's what's most convenient to change. Okay. And the magnetic field is constant and so on. So that's what happens in a generator. That's what happens in your diesel generator. What are you doing in your diesel generator? You're turning a motor, which is turning that wire, which is producing electricity. Okay. All right. So that's Faraday's law. Okay. So now you've learned that if you want to produce an electric field, the one easy way to do it is change the magnetic field. Okay, so you can take a magnet. If you move it relative to this metal wire, if you move it away, it'll induce a current. The bulb will light up. Okay. What matters is relative motion. You can move the wire and keep the magnet stationary, and the bulb will light up. Okay. Here you're changing the area of the loop. You're inducing a current, and the bulb will light up. In this case, the bulb won't light up. If this is stationary and that's stationary, it's not moving relative to it. But if you just spin this thing, the flux through this loop is not changing, and the bulb won't light up. Here, if you pass a current through this wire, it's producing a magnetic field like that. Remember, you stick your thumb out in the direction of the current, and your fingers point in the direction of the magnetic field. So this will produce magnetic fields like that. Okay. And the strength of the magnetic field decreases the further out you are. Okay. So if you move this loop like that, the flux through this thing won't change, and no current will be induced. But if you move it in this direction, the flux through this thing will change, and there'll be a current induced in this in this loop. Okay. So zero current and maximum current in this direction. And in any in-between directions, the current is in between 0 and the maximum value. All right, now we'll talk about the significance of this negative sign. Remember, we already talked about that in the sense of when you take the line integral, okay? So when you did the surface integral, if you're doing the surface integral in this direction, the line integral is you're supposed to take it in that direction, but because of the negative sign, this line integral we took in that direction. Okay. All right. So here's a magnet. Here's a metal wire. When we move this magnet in this direction, what that line integral tells you is the current is induced in this direction. Okay. Now, a current carrying loop, what does it behave like? What is it? I'm sorry? It's a magnet. Okay. And what is the sense of the magnet? So you stick your fingers in the direction of the current, and your thumb, with your right hand, your thumb points the direction of the magnet. So this fella is behaving like a magnet with its north pole and south pole like that. And that's what we're showing here. So look at this. Here's what's happening. If you're pushing this magnet in this direction, the induced current, what is it trying to do? It's trying to oppose it. Okay? So the induced current is such that it's trying to oppose the thing that is producing it. Okay? So the polarity of the induced EMF is such that it opposes the change in flux that produces it. So this magnet is trying to increase the flux through it. The induced EMF is trying to oppose that change. Okay. So similarly, if you pull the magnet out in this direction, the induced current will be in the opposite direction, such that this is a south pole and it's preventing you from moving it. Okay. So you have to do work to bring this magnet in, and the work that you did got converted to electrical energy. Remember, there's no free lunch ever. Okay. All you do is whatever you put in is what you get out. Okay. So in this case, at least the efficiency is 100%, in the sense that all of the work done can be converted to electrical energy. Okay. So in a dam, essentially 90% of the energy of the water, the potential energy, and then the kinetic energy is converted to electrical energy. All right. All right, now we'll look at, so it looks different, but they're actually manifestations of the same phenomenon. So here's a magnetic field into the sheet of paper. We'll take a piece of metal and we'll move the metal in this, we'll move it perpendicular to the direction of the magnetic field. All right, this metal has a bunch of free electrons. So you're moving a free electron in this direction. You're moving an electron in this direction. And Mr. Lorentz tells you, the Lorentz force law tells you, when a charge moves in the presence of a magnetic field, it feels that force. Okay, so V cross B, if this were a positive charge, it would feel a force in this direction, but this is a negative charge, so it feels a force in this direction. So as long as you're moving this guy over there, this will feel the force in this direction. A bunch of electrons will collect here. This end will become positive, and then eventually they will exert a force which, when this force balances the magnetic force, no more electrons will collect there. Okay. Anyway, as long as you're moving this this metal rod in the presence of this magnetic field, you get a bunch of charges collect like that. Charge separation happens, and you see a voltage across this wire. And you can connect a bulb to this voltage source, and cook your pizza. Okay. So how long do charges collect? Till the electrostatic force balances the magnetic force. So the voltage that is developed across this rod is equal to it. You can show that is equal to B times L times V. B is the magnetic field strength, L is the length of the rod, and V is the velocity of the rod. Okay. So the faster the rod is moving, the greater the voltage you develop. And this is for the configuration where you're moving the rod perpendicular to the magnetic field. Okay. If you move the rod parallel to the magnetic field, no voltage will develop. Okay. So if you move it parallel to the rod, to the magnetic field, no voltage will develop. And if you move it perpendicular to the magnetic field, this is the voltage that develops. And then if you move it at an intermediate angle, all you do is take the component perpendicular, take the component of the velocity perpendicular to the magnetic field. Okay, so here's a setup to extract that electrical energy. So again, the magnetic field is into the sheet of the paper. You move the rod, and it turns out that you have to apply a force to move the rod. Okay? You move the rod, and that will induce a voltage through which, and you can use that to drive a current through this toaster or through your oven and cook your pizza. Okay, what we show here is, this is as you move this rod, you see the flux through this thing into the sheet is increasing. Okay, and the EMF induced is equal to rate of change of flux. Okay, and this EMF is equal to that voltage that we talked about. Okay. So as you move the rod to the right, as the current is induced, the induced current feels a force in that direction, and that's why you had to keep applying force in that direction to keep it moving. Okay. What we show here is the applied power times the velocity at which you're moving. That is the rate at which you're doing work. Okay, so the rate at which you're doing work is the force you applied times the velocity at which the rod is being moved. And that is equal to the EMF induced times the current flowing in the circuit. Look at that, that's the electrical power. So the rate at which you did work, okay, the rate at which you did work is equal to the rate at which electrical energy is produced. Again, like I said, no free lunch. All that happened was, what was this? This was just a transformer. It converted mechanical energy into electrical energy. That's all that happened. Yep. So work done by the applied force is converted to electrical energy. All right, so again, so when you move it in this direction, that's the direction of the current. And again, here's how you remember it. When you move the rod in this direction, magnetic flux is increasing into the sheet of the paper. And what is the induced current going to do? It's going to try and oppose that. And so you use your right-hand rule. If the current flows in this direction, you're producing a magnetic field in the direction of the thumb. So if this current, the induced current, is producing a magnetic field out of the sheet, which is opposing the increase in magnetic flux into the sheet. And similarly, if you move the rod in this direction, the current induced is in that direction. Okay. All right, so what we learned was you take a rod and you move it perpendicular to a magnetic field, you develop a voltage across the rod, the metal rod. And the voltage is the magnetic field times the length of the rod times the speed, the component of the velocity perpendicular to the magnetic field. This idea was tested in space. So here's the space shuttle, and here's this wire. So a satellite was tethered to the space shuttle. This is a 20-kilometer wire. 20 kilometers is from here to the US 1 intersection and 95 intersection. So wire that long. And the shuttle, of course, goes at about 8 kilometers a second. It used to go 8 kilometers a second. So that's 8 kilometers a second. The length of the metal rod is 20 kilometers. And what is this magnetic field? That's the Earth's magnetic field. Okay. So about a little less than half a Gauss. Okay. And so the voltage induced should have been about 8 kilovolts. Yeah. And 3 kilovolts was observed. 3.5 kilovolts was observed. Some charge leaks out in the ionosphere, in the atmosphere. So, they wanted to test it out there. Okay. So, all right, you saw that an electric field produced by static charges, the line integral around any closed loop is 0. Okay, for this electric field. That electric field is called a conservative electric field. The electric field produced by changing magnetic field, the line integral around a closed loop is non-zero. Okay, this is a non-conservative electric field. Okay, so that's what we are showing here. So if you have a magnetic field into the sheet of paper and that increases, or if that increases, then you're producing an electric field like that. Okay, and the line integral of this electric field is non-zero. Okay. So you stop changing the magnetic field, what happens to the electric field? Let's say this magnetic field were steady. What would be the value of this electric field? 0. Okay? So that electric field exists as long as you're changing the magnetic field. Okay? And so how do you detect the electric field? You can stick a wire out there, and the electric field will drive a current through that loop of wire. Okay? So this electric field is a non-conservative electric field. Okay? Non-conservative. All right, so again, you saw the generator is based on on the Faraday's law. So here is a magnet, here are permanent magnets. So here in this case, so remember the EMF, the expression for the EMF was d by dt BA cosine theta. Okay. So for instance, so in this setup, what we are doing is we are changing the angle theta. As you rotate this loop of wire, you're changing this angle theta, and you're inducing an EMF in this wire. So if you connect this wire via brushes like this to the outside, the EMF produced, the voltage produced is a sinusoidal voltage. Okay. And here's the form of the voltage. Omega is the angular speed at which you're rotating the wire. Okay, the amplitude of the voltage is N. N is the number of turns of wire. A is the area of the wire. B is the magnetic field strength. And omega is the angular speed at which you're rotating. Okay, so now for a nation. Okay. So here's an amazing thing. So how many different power plants are there in the country? How many power plants? Coal, nuclear power plants, windmills, dams. There are thousands. Here's the amazing thing. So, and you saw that, so each one of them, as they rotate, they're producing a waveform like this, okay? And then you have to feed it to the grid, okay? And you rotate them at different speeds and stuff like that. Anyway, eventually when you feed the signal to the grid, every one of them it has to be 60 hertz, okay? And you have to feed the signal in phase. Okay, everyone have to feed them in phase. Okay, otherwise you'll destabilize it. Okay, so so anyway, that's an art, and you had to produce as much electricity as is being used. You increase the use of electricity, so you have to increase the production in lockstep. Okay. All right, so if you connect this wire, if you're connecting this wire like that, this is the voltage, this is the voltage. If you connect this wire like so to the outside, you get a DC voltage. Okay. That's a DC generator. And of course, if you plug your computer to this voltage, it won't like it. So you have to smooth out this voltage. And you see that, pull that white thing off. Okay, hold that white thing up. Yeah. You know what that thing is doing? That thing is converting this signal to a signal like that. That's its job. So it's converting this to a DC voltage. Okay. And in the next chapter or so, we'll see how it does that. All right, now we'll just talk about a few fun things. Okay. So what did you learn? You learned if you change the magnetic field in a region, it produces an electric field in that region. Okay? And you stick a piece of wire there, and that'll drive a current. Okay, so again, let's remind ourselves of the configuration. So if you change the magnetic field, if you increase the magnetic field like that, the induced electric field is in this direction. Okay? So if the magnetic field increases like that, so the way to remember it is if the magnetic field is increasing in that direction, remember Mr. Lenz says you want to induce, the induced field is such that it's in the opposite direction. Okay? So the current in this direction will produce a magnetic field like that. Okay? All right, so here's a fun toy. Okay, so here's a loop of wire, and here's a metal ring. What you can do is when you close the switch, you have a current, the current initially was 0, and now when you close the switch, suddenly there's a current flowing through this, which is producing a magnetic field, and you suddenly produced a magnetic field through this wire from 0 to a non-zero value. So a current is induced for that flash while the magnetic field is changing, and that magnetic induced current is producing a magnetic field in the opposite direction. So it's like this electromagnet repels that electromagnet, and this guy can fly up. Okay, and when you close the switch, that ring can fly higher than this room. Okay, it's pretty spectacular. You guys have seen this in your bathrooms? What are these things? What is this guy? I'm sorry? Well, it's more than an outlet. So here's what it does. Okay. So let's say you're using a hair dryer or whatever. Okay. And let's say this wire breaks, and this wire hits the casing, and you're holding on to the casing. So instead of the current flowing back into the system, current flows through you to the ground. And you don't like that. And if this thing is plugged to there, if this wire breaks and the current leaks, this device will instantly shut that device off. Okay? So here's how it works. Okay, again, let's see. If you have a wire, if you have a current flowing, hold your right hand out. If your current flows, it produces a magnetic field in the direction of your fingers, right? So a current flowing like this produces a magnetic field like that. So this current will produce a magnetic field like that. And if an equal and opposite current is flowing like this guy will produce a magnetic field in the opposite direction. So as long as equal and opposite currents are flowing, the magnetic flux through this thing will be 0. Okay. Soon as current leaks, so if there's a breakage and current leaks and flows through your body instead, now these currents are become unequal, and the magnetic flux through this thing is non-zero now. Soon as there's a magnetic flux through this, you induce a EMF in here, and with voltage you can trip a circuit breaker and shut it immediately off. Okay, so that's the key. Soon as you detect a magnetic field, you can induce a current in this sensing loop and trip a circuit breaker and turn it off. Okay, so the ground fault interrupter is protecting against electric shock. If current in wire 1 and 2 are the same, then the net flux through the coil is almost 0. However, if current leakage occurs, the flux through sensing coil is non-zero, and the induced voltage triggers a circuit breaker within milliseconds. Okay. So you can induce a circuit breaker within milliseconds. So that's what it does. Okay. And once that circuit breaker is stripped, you can go and reset it by pressing that green button. You'll see one of these things in your garages and in your bathrooms and stuff. Well, yeah. Yeah, so that's what it does. All right, so essentially what we have seen is in this, okay, anytime a flux, magnetic flux changes, you will induce a current in this, you can induce a current in a sensing coil. So that's the basis for sensing any motion. So now you have a mechanism for sensing motion. Okay. All right, so for instance, okay, when this string vibrates, okay, what it does is it produces music, it produces sound. Okay. So what you can do is, here's this guitar string. Okay, when it moves, you want to sense this motion. How do you sense this motion? What you can do is you just magnetize the wire. And as the string vibrates, as this magnet goes back and forth, here is a sensing coil. It will induce a current in this sensing coil. Okay? And then that current can be fed to an amplifier. So instead of having a sound box, you are producing a current which is sent to an amplifier, and it's turned into sound. Okay, through a speaker. So any motion, you just magnetize the thing, and then it'll change the flux through the sensing coil, which will turn into an electrical signal. Okay. All right, so now you know everything how to design a microphone. What does a microphone do? What does a microphone do?
It takes vibrations in the air,
Mm-hmm.
turns them into an electrical signal.
That's right. A microphone turns your voice into an electrical signal. Okay, so when you speak, what are you doing? You send out a pressure wave. And how do you detect a pressure wave? You just put a diaphragm in front. So when you speak, this diaphragm will move back and forth. Okay? So it's like you hold up a paper and talk loud, and this paper is vibrating. Now what's your job? You want to convert that vibration of the paper into an electrical signal. How do you do that? Now you know all the ingredients. The first thing you need to do is attach a magnet to it. So as this thing vibrates, this magnet will move. And how do you sense the motion of that magnet? Put a sensing coil. And what you get is a changing electric field. Okay. So you converted this vibration into a time-varying electric current. Okay. And once you have current, then you can feed it into an amplifier and a speaker and all that kind of stuff. Okay. So this is a microphone. What a speaker does is the opposite. What does a speaker do? You're feeding a current, and this is acting like an electromagnet. So in a microphone, the vibration got converted to electric current. In a speaker, the electric current, this is an electromagnet, and you have a diaphragm with a magnet. As this becomes a magnet, this will make this guy go back and forth, and it turns the electrical signal into sound. Okay. So a speaker and a microphone are opposite things. Okay. So now you've learned a very important thing, how to convert motion into an electrical signal. Okay. What you need is attach a magnet to the object that is vibrating and have a sensing coil. Okay. Okay, so this thing is vibrating. You converted that motion into an electrical signal. Okay, all you did was attach a magnet, and as this thing vibrates, you're changing the magnetic flux through it, and and converting it to an electrical signal. All right, so here's how metal detectors work. You feed a AC signal to a transmitting coil, and AC signal produces a changing magnetic field. So one second it's in half a cycle the magnetic field is pointing like that, and the other half cycle it's pointing like this. Okay. So now let's say this thing is not there. The transmitting signal is inducing a current in the receiving coil. Okay. And so this is a strong signal, and that's the steady state. Okay. Now, if a piece of metal passes in between, okay, in the metal, you're inducing an opposite, inducing a current like that, which is producing a magnetic field like this. And now, the flux through this sensing coil has reduced because of this intervening piece of metal. Okay. Because of this intervening piece, the magnetic field has decreased, and so the induced current in this receiver coil has decreased. Okay, so as soon as a piece of metal passes, the induced current in the receiving coil decreases. Okay. All right, so that's Faraday's law.